So, good morning, and I'm Elena Lacchin, and I'm a PhD student from the University of Bologna. And today I'll talk about the stellar rotation, cluster rotation. In particular, our aim is to study the effects of internal rotation in the kinematical and chemical properties of different stellar populations inside globular clusters. And to do so, the first step is to perform hydrodynamic simulations. In particular, we're interested in the formation of the second generation with stars, which are assumed to be formed out of the rotating ejecta of third-generation asymptotic giant branch stars, plus an amount of non-rotating interstellar medium gas. And as you can see, at 100 megayears, second generation stars are much more confined in a disk that is highly rotating. And this disk is also composed by helium-enhanced stars, which are formed mainly of this third generation ejecta. And in the next slide, you can see the microquantitative quantities. So we can see that helium-enhanced stars of the second generation are rotating faster than helium-poor ones, which are formed not only from third-generation stars, but also from the non-rotating interstellar medium. And we found also that second-generation stars are rotating much faster than the third-generation one. And this is due to the fact that they are also much more concentrated than the third generation. In particular, in the density profiles, you can clearly see that there is a big difference between third and second generations. And in particular, at the end of our hydrodynamic simulation, we find that the half mass radius of the second generation is about 1.5 and is very small in comparison with the one of the third generation. And then these results will then be used to set the initial conditions for the unbody simulations. On the next slide, please. In particular, what we want to do is to model the evolution, the long-term evolution of a cluster that is orbiting the Milky Way at around 4 kiloparsecs from the center. And what we see is that it loses significant amount of mass, in particular third-generation stars that are the less concentrated ones. And from the rotational point of view, we see that after a Hubble time, the third and second generation share a similar amplitude in the rotation and also similar phase. On the contrary, instead, their spatial distribution is still different, and as you can see from the half mass radius that are shown in the density profile. Then the next steps would be to perform other simulations to explore a little bit more the parameter space and then compare our results with observations of present-day globular clusters. Thanks.